So in the previous several lectures, I talked about some simple or rather original quantum algorithms, basically Grover's algorithm and Shor's algorithm, and all its connections and variations to various other kind of things. And I would like to summarize the essential part of it once again, and that boils down to identify what is the basic structure of quantum mechanics which you are using in developing all these applications. So one of them is superposition of states, and the other one is a tensor product. Of components, and of course both of these things are defined in the Hilbert space. So and yeah, the most elementary fact which started the whole subject, the Planck's constant is not zero. In all the algorithms or whatever application, we have chosen units where h cross is equal to 1, and it never appears in the formula afterwards. But if it was 0, then all this business would not have started at all. Now this have certain features which kind of easy to understand even in the classical language, and in the sense that the superposition can be easily understood by looking at wave properties, and this tensor product can be identified with particle properties of distinct objects. But that is a separate point. In quantum theory, both of them exist simultaneously. You can't separate them one versus the other. So it is only for some sort of intuition that you want to develop, you can interpret it that way. But the point is that once you have done that, other properties follow. You don't have to make any new assumption to talk about entanglement. Okay? So it's important to figure out what is the elementary stuff. I have that well covered. Everything else will be constructed or derived from it. And in many areas of physics, identifying these fundamental things is important. So to give another example, look at the theory of relativity. Now, it was discovered, all the transformations of relativity were discovered by Lorentz. That's why they are called Lorentz transformations. But Einstein turned it around and put in very elementary principles that all the laws of physics are the same in any reference frame. That is where the name principle of relativity comes from. And the second assumption is the speed of light in vacuum is a constant. And then he could derive Lorentz transformation starting from this. So the way we look at it, we look at the Einstein's version and we don't look at Lorentz's hypothesis, how he derived his laws. Just because those assumptions look much more intuitive or simpler or whatever it is, there is two simple facts. Laws of physics are same everywhere, and speed of light is constant. And all the algebra will come out after that. The same thing over here. It's important to figure out what is the simplest assumption that you need to make. Other things will just come out after that. Okay, that is the direction which I am pointing out these facts, and it will be important in discussing all the questions related to interpretations of quantum mechanics, which are important part of discussing quantum correlations, Bell's inequalities, all those kind of things. What is the basic structure that you want to have, and everything will come out from it as derivation. So anyway, let me complete this picture. How has these things appeared in the algorithms which I went through? So one version was this question of Fourier transform. How these features were used. So Fourier transform is a n by n times n by 1 matrix multiplication, explicitly defined in the discrete space, and how much effort this thing takes. It requires n square. You multiply these matrices, how many operations are there? Okay. Now we want to take advantage of these features and how this can be reconsidered. So what does the tensor product structures does? That I take the first row of this, multiply by this column vector. It has n operations. Tensor product structure factorizes and that makes operations, so this is order log n. And this is what went into the so-called fast Fourier transform. So this eats up one factor of capital N and reduces it to order log n. It's just n terms completely factorized into log n factors, each having only two components. Then we went to the quantum Fourier transform, which is used in the period finding problem, and it what it uses is superposition of all n rows, and since this is an equal superposition which is used in the period finding problem, this also can be constructed by another log n operations. It's just constructed by using the Hadamard matrix on every qubit, which makes up this capital N components, and it can again be done in this. So overall, this n square when goes to order log n square, and these two advantages remain distinct. They don't overlap. There are two factors over n here. One of them gets simplified by the tensor product, the another one gets simplified by the superposition, and you get boost of both the worlds, and the algorithm collapses from n square to order log n square. Okay. And this is in some sense the best thing you can have. The other algorithm, which was the search, it doesn't have two factors of n, so it has only n items. And so you try to use both of these things and they will overlap. You are not going to get a chance that you get maximum out of this and maximum out of that. You will get something from one and something from other. And so the advantage will be less. It will not be as big as what went inside here. Okay. So what happened in this n items, I again looked at in two different ways. One of them is this factorization. Which is basically binary search, as we look up the words in the dictionary, and then it gives log n to the base 2 because it's a binary search. But now I can ask that, well, what does Grover algorithm do? Grover's algorithm doesn't do any of this factorization stuff. It only uses superposition. And that gives order square root of n. It can't do anything better because there is no particular pattern in the data as available here. This superposition succeeded only because the property of periodicity was there, and that is where you could take maximum of advantage of it in the superposition. Here there is no property, and all you get is this n coming down to square root of n. But you can ask that what I want to use both, and that is available. What will I get if I have log 2n and I want to put superposition on top of it? You only get another factor which is just of 2. Log 4n is half of that. And that is because with one query you could identify 4 objects, and that is the advantage coming from superposition. And I can ask this in the reverse order, that first I did Grover search and now I use a factorization, which is available if I can sort the data in a nice manner. and then it will become maximum thing will give log 2 of root n, and these two are the same. So we can look at it in a different manner, but the fact is that these are the two things which you can play with, and you have to, well, have some trial and error business to figure out how much you can get out of this and how much you can get out of this. You can play with them in different orders, and still you get somewhere. So this is something which you should keep in mind when you look at different kind of algorithms, what is coming from which particular property, and if you find something interesting, then you will have some physical reason to argue where it is coming from.
But can you once again explain why there is a trade-off in sense of in the above case, you are getting the best of both worlds.
Yeah.
And here there is no trade-off. You have to find the
Yeah, because there is only one factor of n. Here what happened is there are two factors of n, and I could make factorization act on one factor and superposition act on the other factor. Okay. Here there was the structure of the problem is that there is only one factor of n, so both of them have to act on the same thing. And that's why you can't get maximum out of both of them. They are not independent, they overlap. And it's not very clear from many definitions of the problem whether you can find this kind of factors. You have to actually work quite hard to figure out what is the property on which you can use this kind of logic. Okay. But I mean, there will be several algorithms which I will discuss probably in the course next semester, the advanced version, and where it will be interesting to identify this kind of features, and they are quite generic. Okay. So now I want to move to the new topic, which is the nature of quantum correlations. Remember that they are still going to come out of just these two features. Nothing more is needed. Only thing is we'll ask questions which are probably of different type. And there comes the sort of puzzles or paradoxes of various types, which are not any contradiction if you look at it the right way, but if you look at it in the wrong language, they all kind of appear counterintuitive and things of that sort. So, how do I attack this problem? And here I have to give basically two Greek words, because that is how people have been asking various questions. One is called ontology and another is called epistemology. What does ontology address? That what really exists in the physical world. Real is not in the sense of description of mathematical numbers, but in terms of physical property. And the question is that this question is asked without paying any attention to observers. It has been phrased in different ways. One of the ways is the moon really there when nobody is looking at it? Okay. So that is a sense in which this question is asked. What is there, whether anybody is paying any attention to it or not? And the strong advocate of this particular type of thinking was Einstein. He wanted everything to be there, irrespective of any other things which is connected to observers or human beings or anything of that sort. It's a fundamental property of nature. Epistemology is the question is, what is observable? By some physical device, instrument, whatever it is, because there is no point in worrying about something you cannot observe. And it's a much more restrictive framework than asking for what is there irrespective of observation or not. Here you are asking a limited question. What is it that you can observe? And here things may be there, may not be there if you can't observe them, and it's not relevant. So again, giving an example for such kind of situation which is common these days is the question about dark matter. Is it really there? And we say that it is there because we can see some gravitational effect of the dark matter. We can't see the dark matter directly, but there is a consequence. And that gravitational perturbations caused by dark matter are observable. So believe it is there. If the gravitational perturbations were not detectable, then whether it is there or not there doesn't matter. There is no interaction with it. And that goes completely outside of any physical theory. You can't observe it. You want to add it, you want to delete it. It has no effect, so why do you care? So that is the game in this that do you believe in this or you believe in this? And people keep on going back and forth in various ways, and the debate is not over, okay, it keeps on going. So what has been tried in various incarnation are the questions regarding to something called the hidden variables. What are hidden variables? They are like dark matter, okay? Dark matter is not actually hidden, but they are properties which you cannot observe. But they are real, in the sense that whatever the system has those kind of properties. So they are And the interpretation of adding this kind of things, well, we human beings are of limited capacity, we can't do everything, and there may be all kind of things present, but it's not within our capabilities, so it's fine, maybe some other different kind of alien people will be able to see those kind of things, but we certainly can't. Yeah.
When you say hidden variables are not observable, we mean that they are not observable currently, but let's say in the future we have some technology which is observing a variable which we thought to be hidden. So that is the becomes.
Yeah, so I can quantify that is not observable by us. And you label it as something which hidden. So the questions of these correlations are all connected to whether such variables exist. Okay, and then if they do, then there is a well-known feature in physics something which knows as effective theory. So effective theories are constructed in lots of different regions or topics in physics, where you don't know a lot of underlying variables. They are all in this sense hidden variables, but you summarize the properties of those hidden variables into some parameters. And as long as you have those parameters defined in your theory, the other things will follow. So in some sense, the whole of classical mechanics can be called an effective theory. You know that there are underlying, say, atoms and various material structures like crystals are there. But you are dealing with classical physics, you use Newtonian laws. You don't care about all those atoms, whatever it is. You take a few properties of all those atoms which come out at the classical level, like what is the mass, or if the material is deformable, what is the elastic constant, what is the density. All those kind of features, they are parameters. If you want to say that how can I understand those parameters, then you have to go down to the atom level, that okay, these are the real physical objects which we are not looking at right now. We only look at the effective theory. So here the hidden variables give rise to what I call observable parameters. And this description is heavily used in statistical physics as well, that you study some materials or crystals, but you look at only the broad property in a gas, for example, what is the pressure, what is the volume, what is the temperature. There are some parameters where they came from, where there are all these atoms of a gas bouncing around, and they created all these kind of effects. We don't worry about it. We can observe pressure and the temperature directly, and we can figure out their laws. Whatever the laws will have, they will have some parameters in it. And if you want to understand those parameters, well, you have to go underneath to the hidden structure. Okay. So this is the exercise, that can I look at quantum mechanics as a consequence of some underlying hidden structure which produces various parameters and properties. I'm not going to directly be able to see this, but say in this case, can Planck's constant come out from some underlying stuff which we don't know? Because we are just using it as a parameter in the quantum theory. And that is the exercise which people tried, and it is a theoretical exercise because everything is hidden. I mean, I can talk about atoms and molecules because now we have the capabilities that we can make certain observations on them and we know that they are really there. But 500 years back, whatever it is, people were working with classical physics. They had no clue about atoms and molecules, but they could still talk about mass and density and things like that. Okay. So the question is that can I get this thing out from something underlying? And it's a theoretical exercise because we don't have any direct connection to it. But remarkably, people are able to constrain the hidden variables by these known properties. Because the hidden variables must produce the effective parameters, and if I don't have the right ingredients, then the effective parameters value will be wrong. And then I can say that such a hidden variable theory doesn't exist. So that is the constraint I have. So and this all the study of quantum correlations is actually, in some sense, analysis of these constraints.
So today we are making, nowadays we are doing this, studying this with an assumption that there are hidden variables.
Well, you have to figure out. I mean, ultimately, it also will go back to that. Maybe there are no hidden variables. We just don't have the capacity to observe anything. So, hidden variable is in the context that there is something there. It's the question of ontology. If I stick to epistemology, I don't have to worry about hidden variables.
So today we are studying quantum technology within being a proponent of ontology.
Yeah, and you ask the question that, do I need to go beyond the epistemology? There are people who say that this is all there is. I don't have to worry about anything more. And for them, I don't have to worry about all these questions. So the question of all this arises if I want to go beyond epistemology and say that there is something more. If there is nothing more, well, stop, full stop.
That's an easy way out.
That's an easy way out, yes. Okay, so now I have to give a specific examples of something which another name. Okay, so this is just a background. So one of these constraints refers to what is called contextuality. Okay, this means observation depend on the setting or the context, which is the word. So this is one of the properties which appears in one particular analysis of quantum correlations. And I will look at this one of the simplest setting available for 2 qubits, nothing more than that. And anyway, all these questions which I'm going to look at only 2 qubits. The simplest system where I can define correlation. If 1 qubit, there is no correlation, 2 parts, and simplest ones are 2 qubits, and see what kind of things are all buried in there. Remember, it's all going to come out of this ultimately, but in different forms. So it's qubits, all you need to know is observables are all connected to polymatrices, nothing more complicated than that. But I'm going to arrange them in a very interesting manner, okay? So look at this set of observables which are arranged in a 3 by 3 array. Where sigma x refers to measuring the x component of this qubit on the first qubit, and this refers to measuring it on the second qubit. Then I write another combination which goes like this, and then there is a third one which I can construct, which looks more or less like its product, but there is a little bit of non-triviality. Tensor product, yeah. I'm not writing the tensor product science, but they are 2 qubit observable. So first of all these objects are Hermitian, so they can be measured. On top of that, they all have eigenvalue +1 and -1. So when you measure it, you'll get either +1 or -1, nothing else. Now look at every row and every column of this 3 by 3 array. The observables on the first row, they all commute. Okay, and they can be measured simultaneously. Same thing over here, they all commute. Here also they commute because this x and y are on different qubits. And everything commutes with that. This commutation with this also is true because there are 2 factors. Sigma x and sigma z will anti-commute, but then the other factor will also anti-commute, and the whole thing will commute.
That's a 4 by 4. Sigma x is 4 by 4.
It's a 2-qubit operator, yeah.
Then how do we say they commute? Like sigma x and sigma x tensor sigma x. It's a 2 by 2, 4 by 4.
Yeah, so when you write down the 4 by 4 matrix if you want, but there are two factors. Sigma x1, what is the commutator with this when you take it across? Well, it will not do anything over here, but you will get a minus sign when you commute through this. Then another minus sign will come when x2 and z2 will go through, and together the two minus sign will combine to plus 1. If you want to write it by brute force, you can do it, that's fine, but they are products and you can just take them across one by one, nothing more than that. So that is fine. And now I ask the question, what if I measure all these rows and columns simultaneously? I can do that because they are commuting Hermitian operators. So what is the total observation that I take some state psi? I measure this, then I measure this, and I measure this, and product of the three measurements. And it is well guaranteed to be the product of the three eigenvalues which I get, which happens to be plus 1. Okay. So let me write down all these things which I said in words. The across rows and columns operators commute and eigenvalues are plus or minus 1. So I measure this row, the product of the three measurements, well, they are all going to get squared, whatever it is, whether it is plus 1 or minus 1, and so the result is plus 1. I take the second one, the same thing. What about this? Well, they are still commuting objects. And if I take this with this, x and z will anti-commute, but y and z will also anti-commute. So the two factors are commuting. And I have to ask now, what is the product of all the three? Well, I take a product sigma x, sigma y times corresponding sigma z. Okay. So I have to be a little careful about the order when I take the product of all those things. So sigma x, sigma y times sigma z. So sigma x, sigma y will give me I sigma z. So there will be a factor of I when I multiply the first qubit operators. And the second one will be sigma y times sigma x, which will actually give minus I times sigma z, the opposite order. So then I multiply with this, I will get minus I, and I and minus I will add up to, not add up to, but multiply to plus 1. And these properties are true for any state. Okay, irrespective of what object I make these operators act on, the answer will be the same. Okay, I am not assuming any property of the state, I am only looking at the property of the operators. So, properties valid for any state psi on which these operators are going to act. Any 2-qubit state. Now I look at the stuff column wise. These things all multiply to +1 because sigma x will get squared, sigma y will get squared. Same thing here. But this is now the interesting stuff. What is the product I am going to get here? Sigma x, sigma y, I will get I times sigma z. Sigma x, sigma y, I will get another I times sigma z. And I square is equal to -1. And that indicates the trouble. That I have possibility to observe either this way or this way. So if I observe all 9 of them somehow or the other, there is a contradiction because if I measure all row wise, the product of the 9 should be +1. If I measure all the 9 column wise, the product should be -1, and that cannot be. And that now creates a problem for this hidden variable picture. That if there are some properties, okay, these values here I just wrote it down as eigenvalues of these things, but suppose there was some underlying theory which produced these eigenvalues and there was some description of it. I don't have to specify what that description is. So this is completely at the quantum theory level. Any deep description I can try to construct, it will end up in trouble. Assuming that all our usual assumption of measuring eigenvalues are valid, which is confirmed by the constraints of quantum mechanics. You can observe all this in any experiment. But what really happened here is a consequence of non-commuting operators. Quantum mechanics allowed the non-commuting operators, this x, y, z, etc., and that non-commutativity could be rearranged in this particular case, or sometimes prediction is +1, sometimes prediction is -1. And how does that get involved here? That I can certainly measure one row or one column, no problem about that. But if I measure this, then I cannot simultaneously measure that. Because this, what is inside here, doesn't commute with what is inside that. So the quantum theory does not allow simultaneous specification of mutually commuting sets. Within each set things commute, but between different sets they don't commute. And that doesn't work. So I can say that for 3 of them I can calculate this, but I cannot say what is the property of 9 of them. That is not allowed. And since the state does not matter, whatever it is, it applies to any hidden underlying structure which may exist. And so the consequence or the conclusion is that QM forbids non-contextual hidden variable theories. The context in which you are performing the measurement plays a role. You have to specify it, and that context is like I'm observing the operators of the first row, or the second row, or the third row. That is the context. Once I have done that, I have no right to specify the other objects which are not commuting with it. And that is in some sense in favor of this epistemological argument that I cannot just put any arbitrary hidden variable. What is observable depends on the context. Okay. So, well, this is one important analysis, and the fact is that it is based not on any property of the state but on non-commuting operators. All that so follows and those operators are defined at the effective level. I can measure them for individual qubits. It puts a restriction.
So it looks like we are trying to avoid uncertainty principle by saying this statement.
I don't have to bring in uncertainty principle. Non-commuting operators automatically will give rise to uncertainty principle from the algebra.
Stating that once the context is fixed, we are not supposed to talk about the other rows
Yeah.
which are non-commuting. And thereby we are trying to evade the uncertainty.
Yeah. Once you fix the context, you have no right to talk about the other stuff which doesn't commute. That is the correct way. You cannot even assign it some hidden variable or any other description. You'll end up in trouble. Context means, in this particular case, can I measure all the 9 simultaneously? I can certainly measure 3, row-wise or column-wise. That quantum mechanical rules don't give any conflict, but I cannot measure all 9 of them. Even by introducing arbitrary hidden variables. So they will end up in contradiction. Okay. So this is one powerful result, and there is a lot more work based on this. There are extensions to larger spaces and multidimensional arrangement of various operators. This is the simplest example which unambiguously demonstrates it, so that is enough once you have a explicit situation. Yeah.
Like now once we have fixed the context, that means suppose we have fixed the row. Like what is the hidden variable associated with that particular?
The hidden variable will be the eigenvalues of measuring these particular objects. Those eigenvalues will be related to some extra degrees of freedom which are buried underlying the usual quantum mechanics. Quantum mechanics, we already know the eigenvalues, but we are assuming that something else is producing those eigenvalues.
So we're not especially specifying the hidden variables, we just assume that.
Yeah, so the eigenvalue will be function of the hidden variable, something, I don't know what that function is. We don't even need to define those functions. Because these properties are for any arbitrary function, you will end up in trouble. Okay. So then, well, another question came that yes, I will enforce this non-contextual version by taking help of another principle of physics. And that is what Bell did, and which is what produces famous consequence which ended up getting a Nobel Prize last year. So what Bell traded off in this version is he removed the question about contextuality. So he took help of the principle of relativity and said that these two qubits are at a space-like separation. And space-like separation means that the distance between them is larger than the speed of light corresponding to the time interval of measurement. Once you put them at a space-like separation and they cannot communicate in any particular way, what happens here is independent of what happens there. So the context question is gone. Is there still a problem? Say, these two qubits are can be measured independently without influencing the two qubits just cannot talk with each other. We took help of relativity, which is outside quantum mechanics. That is fine. You can have an experimental setup of that type. Is there a problem? So now you perform a measurement on some polymetrics on one qubit, some polymetrics on the other qubit, and you ask what is the joint relation between those two quantities, and that still shows up as a problem. So what can you measure? The measure correlations
without influencing, I think they are already entangled or without influencing, which means they are entangled in the first place or
Nothing. It just says that the physically what is happening here is independent of physically what is happening there. What you are asking is not question about the state, about the result of measurement. If I measure some eigenvalue over here, it cannot be communicated to that or the other side. Okay. So correlations exist due to conservation laws. Which are global and unaffected. You have to keep this in mind. That there are global conservation laws and which will produce correlations that have nothing to do with space-like separation, precisely because it is global, covers everything. And this is true even in Newtonian physics. There is one example. Suppose there is a bomb and it explodes. One piece goes in this particular direction and I found that piece. I can immediately say that the other piece is in the opposite direction. I don't have to go and measure it. I know it because the momentum is conserved. Okay. So then the other two pieces are at a space-like separation, doesn't matter. If I know this, I can predict the other part. So that is not the correlation I want to look at. Those correlations always exist. I want to look at something beyond that, where the global conservation laws don't give me any prediction. So the correlations which are looked at in case of Bell inequality are of the form that sigma 1 dotted with A and then the sigma 2 dotted with B. A and B are measurement directions. Because I'm just observing polymetrices on 2 qubits. I have to choose some direction. But to avoid this, A and B are not parallel or anti-parallel. Because then the conservation law will solve the problem for me. I don't want to use that. I want to look at non-parallel direction, some angle. And that has certain features. So that is what Bell worked out, and the state which he chose was the 2-qubit singlet state. Up, down, minus, down, up. Reason for choosing the singlet state, this is actually not done in the original version, which was, well, long history, but the setting of measuring this kind of observables for the first time was discussed by the paper which only goes by its acronym EPR, Einstein, Podolsky and Raison. But that was discussed in the language of this momentum and position, etc. It's too complicated. We wanted to bring it down to qubit, and this was done by another well-known scientist, Bohm. So this is a Bohm version of EPR.
What does A bar and B bar represent? Distance.
Some direction in space.
But
We are measuring the component of the Pauli matrix along that particular direction. It's a three-dimensional space. I can take any.
the qubits were placed by the experimental itself, right? The qubits were like separated by the experimental.
They are physically separated by some distance, and that actually does not matter because of another property that this state corresponds to angular momentum 0. So it's isotropic. No matter in which way you look at it, looks the same. So this is what you call J equal to 0 isotropic state. So it does not select any particular directions at all. You can choose all of them with equal freedom. Okay. So now let me define the correlation function. So first of all, you are measuring this correlation, but they are at a space separation, so I can measure this one and it will give me some eigenvalues. This one, it will give me another eigenvalues, and two things are independent. And the eigenvalues of these things are +1 and -1, nothing more than that. That's what will come out. So measurement result which I can call A and B. Capital and capital B can stand for the two observers if you want. And this is the component which they are measuring, and the qubit structure tells me that those numbers are +1 and -1. I don't know which one, but that's all there is. So now the point is, what is the expression for this object? Well, if I now assume some hidden variables, the correlation I can construct is this. These are unknown objects. What they are, I don't know. they can influence both these observations in some manner. Again, how, I don't know. All I can say is that there is some distribution of these hidden variables which will give me the expectation value. The expectation value is defined as the weighted average over some distribution. And the lambda is now the distribution measure, and this rho lambda is its weight.
So they both are independent. If they both are independent,
Yeah.
then the correlation should be zero.
You can put these hidden variables, I don't know what they are. I know that these two are independent to the extent of the space-like measurement which I make. So that allows me to do A and B independent. This lambda can be far more complicated thing. I have no idea whether there is any correlation produced by lambda or not. I'm just allowing the general situation. The point is that whatever that lambda is, if I took the weighted leverage, it should give me back the expectation value. So this is the integration measure of this lambda is. It could be a discrete sum if you want, but integration is a more general scenario. Okay. And there is one simplification which occurs immediately. Due to the conservation law, that whatever B is, it's minus that A. Because the total spin is 0, it's the anti-correlated system. If I observe something here, conservation law, this must be just the same thing with opposite sign. And so we got rid of this on capital B. Everything is now reduced to the properties of what is at location A, and the two directions are not parallel. Okay. So what can you say about this? Well, the argument will end up very quickly, so you have to look at all the steps carefully. So, Bell looked at this particular quantity. Correlation between A and B, correlation between B and C, and the difference of the two. And the absolute value sign, that is just to make everything within certain bounds.
C means we are taking non-qubit from one position to another position. C means we are taking non-qubit from one position to another position.
Yeah, so you can measure in the different direction. I measure it A, B, C, whatever it is, and ask the same question. Let me put this thing little later, okay? I can do and change this order. Okay, this is more commonly written, and but basically there are three directions, and I'm writing this particular quantities, so this can be just expressed very trivially in terms of this definition by So what happened here, I took this expression and removed some common factors. I have removed this A direction A and A direction B as common factors. So the first term is exactly this definition PAB, which I wrote over here. It has a negative sign on the other side of the equation. And the second term is AC, after you realize that this AB lambda is going to get squared. And then it is a AC and a negative sign. And AB lambda is plus or minus 1. So square is 1. Okay. So this is a same expression as that. So with A, B, lambda plus or minus 1. So now I take the absolute value. And on the right hand side I have an integral. So I can use the triangle inequality. Okay. Triangle inequality says that a linear combination of several quantities with an absolute value is less than or equal to sum of all the individual values. Okay, so this is and this is a sum, but I am going to apply it to the integral, which is also defined as a sum. No problem with that in using that. So this is equal to just absolute value sine this whole thing. There is no problem in that. But now this object, I just put equality sign, and to make full use of this thing, I take this summation, an integral, and put the absolute values inside. Okay. So now I simplify on the right hand side various properties. So this is, I will write it once more, but so some numbers are there, I can put modulus on individual parts. Now look at this expression. These are only allowed values are plus or minus 1. Whatever it is, absolute value is 1. This stuff, this is 1. This could be plus or minus 1. So whatever it is, the absolute value is positive. It could be either 0 or it could be 2.
This thing I'm not getting this left hand side equal to 1.
What?
A lambda, A B lambda.
Because they belong to plus minus 1.
Both are plus 1 or both are minus 1.
Doesn't matter. The absolute value is overall. You can factor as many times as you want, it's not going to change. So this stuff can be dropped. And what about this? Well, that is a weight which we assumed as for the hidden variable. If I take it to be some probability distribution over some allowed set of values, this will be for some probability distribution.
And less than or equal to. And also less than or equal to.
Yeah, this less than or equal to is the,
Rho of lambda also should be
it's positive for a probability distribution. So I get rid of the unwanted terms and particularly the absolute values, and the result is that this is integral d lambda rho lambda 1 minus a b lambda a c lambda, and that is equal to, here actually it's equality because all I'm doing is all the factors are all positive, nothing more than that. And this is also equal, it's 1 plus the correlation between B and C as defined by this rule. And I'm assuming that whatever this weight is, it's normalized. So d lambda rho lambda integrated 1 is 1. So that's the end of the story. And the rest of it is now figuring out what is important and what is not. Okay. So, what is the result? Well, it's modulus A, B, and C. I have to choose some direction, etc., and the convenient choice will be so. So this thing has a 45 degrees angle, so these two are A and B will be root 2 and AC will be 0, okay, for this particular choice. And now I have a answer for quantum mechanics and I will test it against this analysis. So this I can calculate in any scheme I want, kind of a straightforward exercise. If you want to generic ABC, I can write it as a Cartesian product. Sigma x ax plus sigma y ay plus sigma z az. And there are 3 terms here, the 3 terms over there multiplied. So first the diagonal terms, which will be like ax, bx. Well, they are constrained by the conservation law. The same sigma direction I measured on opposite side, there is a relative minus sign because of the state. So it will just produce ax, bx, ay, by, and az, bz. So the diagonal contribution is a dot b. And for the off diagonal one, you have to do a little calculation. It is quotient like ax, by, but that will measure the correlation between sigma x and sigma y in this particular state. And that is 0 off diagonal term with a singlet state. There are no off diagonal correlations at all. So this is the quantum answer for this object, which I defined as this particular combination, that I have this answer. And what is this in this particular case is minus 1 by root 2 for this choice. What does this tell me? That this will give, so inequality tells me this. And it is certainly false. Why? Because 1 by root 2 is about 0.7 or so. And this side will give me 0.3, this is 0.7. So, well, something in the derivation is wrong. And then now the job is to figure out what has gone wrong. until all this stuff is definition, I cannot do anything with plus minus 1. I cannot do anything with the triangle inequality. And the rest of the stuff is simple manipulation. So one answer is that the assumption is false. And that means hidden variables don't exist. And there is another answer which is more interesting. How does this thing work out in quantum mechanics? And I will come to that in the next class. Is I can still go through this provided I interpret this weight as a different object, not a probability distribution. And we have seen explicit construction of that in all the quantum analysis. Quantum analysis works very well where these expectation values are measured using the density matrix. And the density matrix is not a probability distribution which is positive. It has off-diagonal components which are complex. Diagonal ones are all positive. Off-diagonal ones can be anything. So that is another route, but these are the interpretation questions and I will discuss them in detail next time. But the mathematical stuff is all nothing more than this.